Next up is my colleague and friend, Phil Rasch.
Good morning, everyone. I was not paying close enough attention when the invitation to participate in the meeting came along, and didn't good. That's good to hear. I didn't watch my title as carefully as I ought to have, and so this was the one that was assigned to me. I'm going to change that title if I can figure out how to move forward to this one. Since this is a bringing it all together slide, oopsie daisy, a bringing it all together session, then I thought maybe what I'd do would be to spend some time talking about aerosol and aerosol-cloud interactions in climate models, and tell you what I see as being on the climate modeling front for the current years and maybe the next couple as well, and maybe where there's some opportunities for improvement. Before I go forward, I want to acknowledge a good deal of the work, virtually all the work in the weeds has been done by my colleagues. I've had the pleasure of being engaged on many of the topics that I'll talk to you about today, but these people deserve most of the credit. So my plan for the talk is a rant on a paper that's probably familiar to most of the people in the room here, titled Uncertain Then, Irrelevant Now, and then spend some time talking to you about developments in clouds and aerosols and climate models, and focus some attention on process level improvements, and also recognizing that I think, in my opinion, we're not spending enough time addressing computational issues in climate models that are compromising our ability to do aerosol-cloud interactions as well. So for those who are not familiar with this paper, the top one is the one which pushed my buttons by Bjorn, and this was a commentary on a paper that Ken wrote a year ago, and maybe the first button it pushed is the characterization that aerosols were a joke in the climate system, but there were many things in there that I was a little uncomfortable with. So I'm going to go through a few quotes before I launch into the rest of my talk, similarly to what Chris did in his opening presentation yesterday. So Bjorn's characterization was that most of the uncertainty associated with cloud-affected aerosols can be attributed to emission rates and aerosol precursors from natural sources, which I think there's elements of truth to all of these things, that their role probably played out a century ago, and it's become irrelevant to understanding present and future changes in global climate. Poorly constrained natural sources determine the state of the pristine atmosphere and thus are dominating the uncertainty and estimates of radiative forcing. And that, indeed, the buffering that we've heard discussions about is present today, and that the current atmosphere is relatively insensitive to changes in tropospheric aerosols. A repeat of that. So what might be missing from Bjorn's interpretation of what Ken said? The first was just to recognize, I think this is correct, and over a beer last night I offered Ken the opportunity to correct anything that I say if I'm managing to misinterpret what he did, but he was focused primarily on the first aerosol indirect effect. And one of my reactions as well was some of these fundamental issues have been known by this audience and the climate modeling audience for well over a decade at this point in the game. Ken did not address ice effects or things like invigoration. His conclusions were based on a subset of processes that we know to be important in the climate system. A focus on the present and future forcing neglects the importance of understanding the historical forcing that in turn confounds our ability to determine climate sensitivity. So the fact that we don't know what role aerosols have been playing over the last century confounds our ability to know how rapidly the planet would warm in the absence of that aerosol forcing. So it doesn't mean that aerosols that their role today is not important as well. And lastly, I think there was sort of a flaw in the logic as well, where the statement that A depends upon B and C, and B is important, where B is, well, I'll get to that. That implies, therefore, that C is unimportant. And in this case, A is the climate change in the presence of anthropogenic forcings, B is natural emissions, and C are the anthropogenic emissions and process representations. And these were some of the partitioning that Ken indeed used in that paper. So I'm just going to now jump through a few of the places where there were some uncertainties that were definitely addressed in Ken's study, but that perhaps weren't telling the whole story. And one of them I'll start with is the role of biogenic secondary organic aerosols. So Ken assigned it a relatively low uncertainty compared to other of the agents that have been contributing to climate change. But if you, and the red bars here are ones which Manish Srivastava has assigned to it, where this is not any attempt to be thoroughly quantitative the way the Karslav paper was, but rather just to indicate where we think some of the amplitude of the uncertainties with respect to secondary organic aerosols are, and I'm going to spend a couple of more minutes reminding you about why. Hopefully most people in the room have seen this before. I'm not going to spend any real time on it except to point out that the green segment of these pie charts is indicating the contribution from organic aerosols in a bunch of places around the world that are relatively polluted. And if you look in more pristine regions, this is from another study, the organic aerosols are again playing quite a large role. They're a large part of the mass budget of aerosols, and they're very simply treated in climate models today. Yep, there's a huge amount of complexity to the chemistry of those aerosols and their potential role in aerosol-cloud interactions. So traditionally, climate models have been treating these aerosols as semi-volatile, and we in fact bypass virtually all the chemistry that's really going on in them, and most of the models participating, for example, in the IPCC are simply prescribing the emissions and then characterizing the products of those emissions, the gaseous emissions, and characterizing the products of those emissions through yields. But we know that approach is really wrong, and a lot of recent data has shown that once the aerosols form, they're not semi-volatile, but that they're really quite often now looking like sort of tarry substances. And so people have begun to explore these features in climate models. I'll show you one study. For those of you who aren't familiar with it, the secondary organic aerosol precursors are emitted as gases, which then undergo a really complex set of chemical evolution, which are often characterized in climate models through their volatility basis, or by dividing them into a set of sort of characteristic gases by their volatility. And they gradually become let's say, take on a lower volatility, and these assumptions have historically still had some real challenges to them. There's a Manish has, Srivastava has, along with his collaborators, Ala Zelenyuk, has demonstrated that another useful way of characterizing this, and Barbara Finlayson-Pitts has also done really fundamental work on this, is through a recognition that this evolution can be described through the species functionalization and subsequent fragmentation of the long chain molecules that the gases consist of. My only point in showing you this diagram, really, I'm not the best positioned to talk to you about the subtleties of this, but to indicate that there are huge uncertainties in the chemistry that's taking place in these aerosols right now. And and also to indicate that in the simulations, which I'm going to show you in the next few slides, that one set of assumptions has been made about an appropriate description of these aerosols, but there are many others that are, well, there are lots of uncertainty in the characterizations that we're using right now. So the bottom line for this thing is that the standard distributions of aerosols, which are similar to those that are used in most climate models today, have changed when we changed the picture of this. And there's in the paper that just appeared, or that's in press right now, Manish has described a variety of different assumptions that have been made for the secondary organic aerosols. And for the ones which fits the observations best, his assumption is, or his conclusions are that the contributions from a fixed set of emissions are about 3 times higher. The secondary organic aerosols are about 3 times higher than they would other be with lifetimes that are twice that we've historically assumed. There are significant consequences to this. For example, in the high latitudes, climate models typically have had very little organic aerosol. The solid black line here is indicating the observations, the mean of the observations, or the mode of the observations, with the gray bar here providing the range. The revised aerosols are at least getting the plumes in the right place, and the amplitude is much more realistic as well. Another point that we wanted to make is that aerosols of biogenic origin are actually being sensitive to the presence or absence of anthropogenic emissions of other things as well, the oxidants themselves or the presence of sulfur, ammonia, and NOx, for example. And what I'm showing you here is a study from Hoyle et al. Where they're showing you the secondary organic aerosol yield as a function of the presence or absence of NOx. And for high NOx regimes, this ratio goes down. The yields are about a factor of 3 higher than they are in more pristine environments. So this is also currently ignored in most models today. Now to switch gears to another natural aerosol which has not been treated very comprehensively in climate models. I'm going to show you some work from Susanna Burrows that I've had the pleasure of participating as well, where we're beginning to recognize that sea spray contains more than salt, that has an organic contribution, which changes the composition of these kind of aerosols. And we've attempted now to treat bubbles which are rising through the near surface layers of the ocean and collecting surfactants. When they burst, they carry along the organic matter as well. If you explore the behavior of the organic components of the sea spray, you can demonstrate that it depends upon the biota that live in the surface layer and their subsequent byproducts significantly. We have historically, when we've tried to treat these kind of aerosols, we make them dependent upon chlorophyll. But there are other components, organic components, which are also playing a role here. And Susanna has attempted to explore what the sensitivity of the subsequent the aerosols produced by this process, what it has on the biota on the that is the biogenic activity in the oceans that are taking place. So what I'm showing you here are the correlation between monthly mean chlorophyll and the submicron organic matter fraction based on different assumptions about what the ocean is doing. And I just want to indicate to you that the correlations, the organic matter can be quite different depending upon what assumptions you make about the ocean biota. I'm going to jump now to just point out to you that there's also a lot of evidence for that aerosols in the present day are still having a strong effect on clouds, even in situations where there are Bjorn might make the argument that we're living in a buffered world. So there was a nice paper by Elon Karen and Graham Feingold was an author on this paper. I hope you know it, but it's basically just pointing out that higher aerosols amount are in this case also associated with higher rain rates in certain kinds of clouds. And Danny, of course, has made lots of arguments about the role of aerosols in invigorating clouds, changing their precipitation rates and the depth of convection also. Elon also did another really interesting study, which I won't try to describe to you in any detail, but if you indeed read the red lines here, on average, the cloud fraction decreases to about 1/8 of that seen in clean conditions as the optical depths increase. And I think that I'm offering you up these examples as places where we can begin to challenge our models to see these are, in some sense, correlative studies showing the presence of aerosols as having an impact on some aspect of the climate system, but there are things which we can use to challenge our climate models today in ways similar to what Ken was suggesting in his starting talk also. The distributions of aerosols in climate models now are still quite crude, but we're spending a lot of time attempting to improve them. I thought I'd show you one example from a study that Hai Long Wang did, and this was on a poster he showed yesterday afternoon. Distributions of aerosols in the remote atmosphere are frequently quite unrealistic in climate models today. The standard CAM aerosol distribution is about 3 orders of magnitude too low and shows the wrong seasonality. These are surface concentrations of black carbon that I'm showing you here. But with more realistic cloud models, we've shown that the distributions could be improved, and with careful attention to the cloud microphysics and scavenging and cloud distributions, we've been able to really improve this situation. So at this point, we're getting the right seasonality, and we're within an order of magnitude of the right amounts of aerosols over the seasons. We know that changes in aerosol-cloud interactions are sensitive to model resolution as well, and I'm showing you 2 simulations driven by constrained meteorological fields. So these are under the same winds are being driving them at about 200-kilometer resolution and 25-kilometer resolution. You see significant differences in the evolution of the aerosol species. And I'll just point out to you that the color map here is going by orders of magnitude. The amount of aerosol reaching high latitudes is quite sensitive to our horizontal resolution. And precipitation distributions are also very different. You'll notice the maximum value is about an order of magnitude higher in the high-resolution simulations. And this changes the character of the aerosol scavenging and the transport processes as well. So we know horizontal resolution makes a difference. Ian, how am I doing on time here? Good, okay. So when we've begun to explore the susceptibility of those clouds to resolution, I'm showing you panels here of estimates of the cloud susceptibility as a function of resolution, and it's quite difficult to read it, but this is 2 degree, 1 degree, half degree, and we've actually done quarter degree simulations as well. The susceptibility is sensitive to the resolution. It depends on the cloud regime also. So we're aware of this. We think it's worthwhile spending time focusing or exploring this in more detail, both in cloud, in models as well as in the observational data sets. And Graham has done it with McComiskey, as Allison has also done very interesting things in characterizing these processes as a function of resolution. Lastly, I'm going to just remind you that we are aware of some of the serious biases that we see in our models today. I'm showing you here let's see if I can say it right, the sensitivity of liquid water path or of precipitation to liquid water path for a variety of different estimates from satellites, from models that use much more realistic characterizations of up and down drafts, but quite similar characterizations of the aerosol processes themselves in the in a model in which we've embedded a cloud resolving model in every cell of a GCM, and contrasting that with the current characterizations in our traditional convection parameterizations. And what one notes is that the current models are very sensitive to the presence or absence of aerosols, much more sensitive to the presence or absence of aerosols than the more realistic treatments of clouds and convection in GCMs that are possible in the next generation models. And then the last thing is just to remind you that numerical methods matter, and I'm showing you one study that we recently completed looking at condensation, well, at numerical methods in aerosol processes. In this case, it was the evolution of the sulfuric acid and the formation of new particles for a relatively simple differential system, which made really significant differences to the distribution of the sulfuric acid gas and to the aerosols themselves. And just to point out that this same sort of equation is also absolutely relevant to clouds and cloud processes. So what we did show in that paper was that the traditional treatments were quite inaccurate, that by substepping this differential equation in time and taking smaller time steps, that it was possible to achieve much better accuracy, but that there were just alternate numerical methods which would achieve very high accuracy even in the absence of substepping. So my team and others, for example, Andrew Gettleman and Hugh Morrison, have been spending a lot of time thinking about numerical methods to make sure that we're actually rendering the equations that we're using, that are intended equations in continuous form in a reasonably accurate way in GCMs. But I don't think that that's being done very well today. So I'm just going to jump back to some of Bjorn's conclusions and react to them. I think all of us acknowledge that our simulations are very sensitive to natural sources, and we're focusing a lot of attention on them and attempting to improve them. My sense is that aerosols are not irrelevant to understanding present and future climate change. It's easy to identify aerosol impacts today, even in situations where one might assume that the response is we're working in a saturated world. And I also want to point out that if indeed we manage to reduce our aerosol emissions, then if these aerosols were playing a role, then they'll go away. And finally, I think whether or not the aerosols are buffered or not, I think the jury is still out. There's lots of evidence for aerosol impacts on clouds and climate features. Reduction in current anthropogenic emissions could be important, and what they're doing today is confounding our understanding of other components of the climate system. So with this, Bjorn's concluding paragraph, I actually agree with quite closely, and I think many of you came to the same conclusion, that a fundamental understanding of important processes really is critical. There isn't going to be progress without a focus on those processes and using observational constraints. But I think it's a mistake to ignore the aerosol contributions. So I'm going to close there pretty much and leave you, though, with one last slide and open it up for questions. But we had geoengineering in the title. You may have noticed that Hugh Coe, when he gave his talk yesterday, showed some of these same figures. I just wanted to let you know that Rob Wood is leading an activity which many of us are engaged in, Hugh and Chris and others in the audience, to contemplate the possibility of an experiment relevant to geoengineering, but also very relevant to the things which we're talking about here. There's a web page associated with it, and if people want to follow up with me or Hugh or Rob in the question and answer session, then we can do it then too. And with that, I'll close.